Hello, everyone. Welcome. We're excited to have you here. Sangha is a staff data scientist at Chegg. She works on problems related to school and college education to sustain and improve the learning process. Her work involves computer vision, deep NLP analysis, data pipelines, and machine learning. In this session, she will present Computer Vision for Beginners. Just a quick note to please post your questions in the Q&A box instead of in the chat. Sangha, a reminder to start your timer, and off to you.
Thank you, Shivani, for the wonderful introduction, and thanks for having me. My main goal in the talk would be to get people started in the space of computer vision, and to provide you with some applications and some tools to do so. So here is a brief outline of the talk. I will go through applications. I will also dig a little deep into the deep learning architectures. I'll talk about metrics. And then if there is time, I will talk about object detection as well. So without much ado, let's get going. So what is computer vision? So if we want machines to think, we need to teach them to see. And by see, we just don't mean like see numbers, but we need to understand what the pixels mean. And here you see an example with a bunch of pixels with some values. So we just don't want our computers to understand what these values are, 239, 214, but also to conclude that this is the photo of Abraham Lincoln. That's the general goal. Let me go through some examples where computer vision is used in our daily life. So we have all done Google search, and a very go-to thing for a lot of the cases is you actually search for things and you look at images. This is very convenient, and this is driven by computer vision techniques, but very specifically driven by image similarity. The next application that I wanted to go through was healthcare. So on top you see a very complete system where you have imaging for the whole body. And this system would not just have computer vision, it would have NLP parts as well. But the idea is in real time, you have information from different parts of the body. You have like recordings for heartbeat and other things, but you have imaging. And at any time, this helps with cancer screening, disease diagnostics, surgical assistance, etc. I also wanted to go through like a specific case where computer vision can be used effectively. And I've taken this example from Kaggle. So this is detecting diabetic retinopathy. So diabetic retinopathy happens when some lesions happens in the retina. So in this image, you see like the normal retina, the healthy retina looks like this, and then the diabetic retina actually looks different, and there are like spots on it. And the way this is detected is humans go through the images, and they tell you which image has diabetic retinopathy, and then that information is uploaded in a system. Typically, this takes time, and it's not scalable. And a huge amount of people in different parts of the world actually have this issue. So having like a model that classifies an image as having diabetic retinopathy versus not would be a very scalable solution. It's also like it's something you can practice on. You can download this data from Kaggle and build this classifier yourself. The next application I'm going to talk about is education. This is what I do for a day job, so this is very close to my heart. And I will go through like one case where, let's say your child is drawing pictures of rockets. Now your computer vision model takes these pictures and classifies them, and so now you know that in school, like the school knows that the child is drawing pictures of rockets. And based on that, they can develop this profile where you can say that your child is very excited about space. They're interested in astrophysics. And you can give this information back to the parents, so the parents can talk more about astrophysics and rockets at home. So this is like one example. Gaze analysis is also another really nice example where you can actually look at the eye movements and sort of get an idea of whether the student is listening, whether the student is actually understanding what material is being presented to them. And then there can be various types of personalized learning experience where you can have learning paths and from there go to career paths. Collaborative learning is also something that can be derived, where pairs of students based on their learning styles can be put together. The next example that I'm going to talk about is the most common example that we've seen with computer vision, that of self-driving cars. So self-driving cars needs cameras, radars, and lasers to allow the car to perceive the world around it. And it mainly uses computer vision in the form of object detection and classification. For these systems, like, your models have to be extremely fast because you're taking so many images at the same time and constantly giving outputs toward these images. And finally, what I would like to talk about in the application space is a lot of the time our mobile apps actually give you the opportunity to take a picture and upload it and get different kinds of information. So one example I have here is that of art. You take a picture of an art and a certain mobile app tells you, who is the artist, what kind of painting it was, what genre, etc. Another, like pictures of food, people take them for various reasons. One of the reasons could be health and fitness, where you take the picture, you determine this as eggs and bread, and you give back how much calories they contain, and that could be helpful. Another example is from insurance point of view. When you have collisions, you can take pictures of them, and then that can get used in different applications, insurance being one of them. And finally, in education, also you can take pictures of whatever your learning material is, and then either you have questions around it or more in-depth concept analysis for that can also be done. And this is something you can also use to actually build your first computer vision model. I don't know about you, but I tend to take a lot of pictures of food. So one model could be you distinguish between this is a picture of a food versus not. So it's a binary classification. And once you have the pictures of food, you can also have a more detailed model which tells you, what kind of food is in your pictures. And you could have this for other fields as well. So I will stop a little bit to see if there are any questions.
No questions right now, Sangha. You can keep going.
Okay, cool. So the very broad computer vision techniques, mainly on images, are image classification plus localization. So classification tells you whether this is a picture of a dog or a cat. Classification plus localization will tell you that this is where the cat is situated. And then object detection is the next step, where you basically find out how many dogs and cats are there and draw boxes around it. And then instant segmentation is the case where you actually go and get the pixels that are related to every object. I will talk mainly about classification, and if there's time, I will talk a little bit about object detection as well. So what is classification? So the idea of classification is that you have an image, you have a bunch of pixels with values in them in the red, blue, green bands, and all of those images, get converted into some kind of numerical list. And then your classifier will tell you, this is 85% cat, 12% dog, 2% cat, 1% mug. So basically, the idea is you take an image, you put some categories on top of it. So what does a classifier look like? So this whole system is a very typical computer vision deep learning architecture. And here what you see is you have an image, and then the first things that are like the backbone of computer vision in some sense are the convolution neural networks. The main idea behind convolution neural networks is that these are units that are really good at extracting features from your images. And then you have some pooling on top of it, which is basically a system to downsample. And then you have like several layers of these. And then at the end, you have a few fully connected layers that give you the final classifications. And here, I'm assuming that you know what each of these means. But if this is not clear, think of this as different units in deep learning. And the main thing to take away from here is that you need like units of convolution layer to do any kind of deep learning classification on images. So now I want to go back a little and kind of look at the history of deep learning classification that had been happening. So it kind of started with LeNet in 1998, and then there was AlexNet, and then there were several other networks that came out. And what we saw with time is that the networks got bigger and they got more complex, they got deeper, and correspondingly, the performance of these networks actually improved. So I will talk about 3 of these networks here. I'll talk about AlexNet because it was one of the pioneering networks. And then I will talk about VGGNET. And finally, I'll go into RESNET. So before doing that, I also wanted to give you a sense of what the performance was. So this performance is measured on Imagenet data, which consists of data of like dogs, cats, different mammals, but also airplanes and other objects. And the main thing I wanted to show here is that your first model had like 54% accuracy, but by the time you were at inception before, the accuracy increased to 80%. So like the last 10 years have been sort of in some sense, the golden era of computer vision. Another thing I wanted to share was the size of the model versus depth. Here, the x-axis is the depth, and the y-axis is the accuracy. So as we've seen, like the latest model, which was Inception, had the highest accuracy. But when you're actually practicing and you're trying to get a model to run fast and give you some results, one thing you have to keep in mind is how large is the model. And models that are really large take very long to train and are not a good starting point. So for me, the starting point has always been RESNET 18. And even though it has like 70% accuracy versus 80 for some of the highest ones, it's fast. And that that helps you progress in a project and look at your end results. And then you can once you're happy with the end result, you can go back and improve your accuracy with larger models. Before I go into details of the network, are there any questions? Maybe not.
There are. I'm sorry, I just had a little unmute issue there. So Crystal is asking, thank you so much for this talk, Sanghamitra. What is one of the biggest challenges with utilizing computer vision on a mobile app?
So one of the challenges that you have to face is your model has to work within the computational constraints of the mobile app. Another factor that you have to keep in mind that your models have to also be very fast. So in this case, like choosing a model that's small and that does not require too much memory, too much compute would be very ideal.
Awesome, thank you. And then our next question is from Sankalp. He asked, why do we increase the number of channels as we decrease image size?
I don't. What do you mean by channels? I don't follow the question because you have RGB channels, which is more or less constant for a colored image.
Sankalp, feel free to clarify in the chat or as a follow-up to your question. Okay, maybe we take this at the end. Sure, sounds good. Feel free to clarify until then and you can keep going.
Okay. Okay, so let me go ahead with AlexNet. So the first architecture that I wanted to get into was AlexNet because it was one of the firsts where the accuracy had sprung up by a lot. And the main thing that was novel here was this was 8 layers deep, so it's not super deep. It had a few layers of convolution, pooling, and then a few fully connected layers. Some of the new things here was data augmentation. So in data augmentation, AlexNet used flipping, jittering, cropping, color normalizations. And this was also new compared to what had been done before, which increased the performance by a lot. This helps because if you have a finite amount of training data, basically this increases your training data 4 or 5 times because now you've created new images from your existing training data. So yes, what was new here was like a new activation function was used, and dropout regularization was used, and also like 8 layers was fairly large at that time. So it worked well, and basically the news had spread out that a revolution is underway, CNNs have arrived, and there's also special GPU hardware. So here, like the interest sort of brings up in computer vision. So the next architecture that I'll talk about is VGGNET. And what VGGNet did was it basically made the network much deeper. The individual convolution units were made much smaller. So in AlexNet, they were much larger. Here, each of them were 3x3, but then you stacked a lot more of them, and this produced a higher accuracy. And here, like these examples are of like one which has 16 layers, another which has 19 layers. And basically here it really pushed the envelope, and there was like a really large jump in the accuracy. But here it's also important to remember that as your networks get deeper, they're more expensive to train, and they are very slow to evaluate, and they're very slow to infer from as well. So the next thing that I want to talk about is like here, I have skipped a few of the networks, but so far what had been happening is that basically newer models were coming in, and there were some like minor tweaks, but basically people were going deeper and deeper. So the question was, if you just kept going deeper, you go like 100 layers deeper, 50 layers deeper, does that mean your accuracy goes up? And the answer to that is, for a simple network, it does not. And that's because as you go deeper, for doing gradient descent, you basically multiply n very small numbers or n very large numbers. And this leads to vanishing and exploding gradients. So this problem needed to be handled when you went beyond a certain number of layers. So to deal with this, RESNET was like one of the first models that came up. And what it did was it skipped 2 layers and sent the input out to a layer that was further in. So basically, even if your linear layer was sending out very small numbers, you were also adding to the input the information from 2 layers ago. So that way your number was never really going too less. And this architecture kind of brought out the domain in which your deep learning network could go much deeper without having the problem of vanishing gradient. And we kind of see that in the performance. So here on the left-hand side, you see the performance of a plane network that kept going deeper, and then at one point the accuracy did not get better, or the error did not go lower. On the other hand, when you use RESNET models and you went deeper, basically your error kept down. And after this, there have been several models with fairly complex networks. And in a lot of the times, the idea was to connect different parts of the network to improve the performance. So this was kind of revolutionary in the sense of how networks changed the architecture, and you got the opportunity to bypass 2 of the layers. This was a prize winner again, and it has some similarity with biological visual cortex, and it behaves like an ensemble of shallow networks. So there is scope to parallelize in this space as well. So now I kind of want to go into image classification pipeline. So far we have looked at like some models that have done really well in the past, and then some applications which use computer vision. So how do
we have a quick question. Sorry to interrupt you,
yeah.
But Sankalp was able to clarify, and we have one more that has to do with the section you just started. Okay. So I wanted to kind of so Sankalp clarifies his question, which was originally, why do we increase the number of channels as we decrease the image size? And he clarified to say, RGB channels are for the input images. As they pass through the network, the number of channels/features keep on increasing. So when he's using the word channels, he's using it to mean features, it seems. So.
Okay, so like the convolution network basically gets you, how should I put it? is able to extract features from the images, and then the pooling layers downsample them. So basically, as you go through the layers, you only pick out the features that are most relevant in some sense. And if you think of facial recognition here, so when it goes through like the first layer, you're able to get like the curves or the lines, and that information is fed into the next layer, which probably gets like the idea that these two lines make up an eye. So that way the information is reduced as you go through each of the layers.
Awesome, thank you. And then our next question is from Kevin, and you might be covering this more as you continue on in your talk, but Kevin asks, for computer vision in practice, do you recommend writing scripts and importing packages with pre-trained models from TensorFlow or PyTorch?
Yes.
Or would you recommend using cloud-based solutions such as AWS's Recognition?
Okay, so yeah, that's a very good question. And the answer is both in some sense. So it's not very difficult to import, like install packages like PyTorch and import pre-trained models and like create, I mean, this is actually what this slide is about, and create a pipeline that, that gives you a classification result. However, Amazon Recognition sort of makes this even more higher level. So you can basically pull facial recognition if that is the problem you're trying to solve, and it will do something for you. Or so things like Amazon Recognition or Microsoft Azure, they have built-in applications that might actually be the application that you're trying to solve. In that case, you will save a ton of time by using like one of these programs. However, a lot of the times, the specific problem you're trying to solve is not exactly the solution provided by the package that you're using. And in that case, building a classifier to solve the specific problem makes sense. Does that answer your question?
Thanks, Sangha. I think that does. Kevin, if you have any more questions or clarifications, feel free to post a follow-up question. I'll let you keep going.
Cool. And I am actually not speaking about Microsoft Azure or Recognition in this talk, but they do have some cool applications. So it's definitely a good idea to research and look into what is provided. So this particular pipeline, I have written PyTorch in this slide, even though this slide does not have anything specific to code. So you could do it in TensorFlow or Keras. But the idea is initially you do some data pre-processing, and I have a slide that goes into that part as well. Then choose a classification model. My go-to model is RESNET, but basically my advice is choose any model that's not too big, especially if it's your first training attempt. And then I have written CPU in the first phase, but you could also use GPU for the green part of the pipeline. But the idea is here you don't train your model, you freeze the layers, you extract the features. You could put like a classifier like support vector machines or logistic regression on top of it, do your classification and measure the performance metrics. And this pipeline is useful when your data is similar to the data that the pre-trained network was trained on. But the other point is also there may be a time when you have very little training data. So let's say you have 100 objects as your training data. That is like too small to do fine tuning. So even if your data is different from the pre-trained model, just freezing the layers and going with a classifier would make. But then the other line is fine tuning, and in this case, you should make sure you have enough data, enough training data for your classification task. And in this case, the first step is data augmentations, which is the flipping, jittering, color normalizations, etc. Luckily, packages like PyTorch actually give it to you out of the box. So all you have to write is .normalize. You'll get like one of the data augmentations. In fine tuning, you have to make sure the layers are not frozen, and then add the final output layer, which could be a softmax or a linear layer. Choose your optimizer, which could be SGD or Atom. And it's a good idea to play with these parameters. Train until validation accuracy on validation data converges, and then finally measure your performance metrics. Next, I will go through some code, and these codes are mainly from Pytorch tutorials, so you will you will have access to them. So the first thing to remember is it's very important to take your training data and split it into train, test, and validation sets. And here I have some numbers which were based, these numbers are not set in stone. Your training data should be around 70 to 80% of your data. And then there should be some test data, which is also not very small, and then some validation data as well. And it's important to remember that the test and the validation should represent the nature of your data overall. So let's say you have 20 classes. You should make sure that each of these classes have enough representation in your test and validation data. And it's also important to have all of these three buckets and not just have train and test, because validation data is something on which your accuracy is constantly calculated in each epoch. And based on that, your basically your parameters are updated. Whereas the test data, you don't touch it throughout your training process, and at the end, you measure your accuracy on the test data. So that's your final performance mean. And here the code is mainly for doing this test training validation. The other thing that I wanted to mention was data augmentation. And data augmentation basically is a process of cropping, flipping, changing the colors, rotating, and resizing your objects. And again, like in modules like Pytorch or Keras, you can basically call these functions and it'll do it on your data. And this increases your data manyfold. And this is also like another part, like this is mainly code, but this is like a part of the work that you have to do in most modules, definitely in Pytorch. That is, you have to take each class, images from each class, and put it in separate folders inside train, test, and validation. It is a bit tedious, especially if you have not worked on computer vision before. It is like something new that you have to do. And finally, the training process is like a process of choosing your model, which in this case is RESNET 18, choosing your output layer, and then choosing your loss function, your optimization function, and then you have the training code to train for each layer. Here, the important thing to remember in the training code is that basically you have tags attached to your data which says train and validation. And when you're going through your validation, you should make sure that you do not update any parameters. And again, all of these codes, like you can find them online in Pytorch tutorial on fine tuning. The other important part to remember to do when you're coding is the question is whether to freeze or not to freeze the parameters. So if you're doing feature extraction, and feature extraction is important in like problems related to similarity or problems where you're not doing a full-on training, pre-trained weights should be frozen. However, if you're fine-tuning, make sure that the weights are not frozen because you want the parameters to be updated based on your training data. So I will stop again and take some questions if there are any.
Yeah, we have a follow-up question from Kevin. He's asking, does freeze layers mean that the weights aren't updatable and only used for predictive purposes, whereas unfrozen layers means the weights are tuned/trained based on your data?
Yes, that's exactly what it means. To freeze means none of the weights change. So it's just like the final layer of softmax or logistic regression or something like that that takes the layers, that takes the information as features and does a classification based on it. And with fine tuning, all the parameters, and sometimes these models have millions of parameters, so all the parameters change. And that's also why it's important to remember that you need quite a bit of training data to justify fine tuning. The other thing also is that when you do fine tuning, your initial conditions are your frozen or not frozen, but your initial conditions are your pre-trained values for the parameters. Okay, so I have like 9 more minutes. I think I will go through the metrics and then take questions, and I will skip the object detection part. So a very important part is understanding metrics, understanding how your model is performing. And the model performance does not mean the same thing to everybody. So for instance, in a problem like cancer detection, you kind of want to get all positive cases, and it's okay to get a few ones that are negative rather than miss a few patients that have cancer. Whereas for some other problem, it might be important that you only get the positive cases, and like your data is not diluted by false positives. So let's define these terms. So true positive is number of observations that model correctly predicts as a positive class. False positive is number of observations where the model incorrectly predicts positive class. False negative, again, is where the model incorrectly predicts negative class, and true negative is where the model correctly predicts negative class. Now, this is for binary classification, but this gives a good view into the whole metric space. So now let's define these different metrics. Precision, which is what percentage of the positive class is actually positive. Recall, which is what percentage of the positive class gets captured by the model. So in case of cancer detection, you want a model that has high recall. And then accuracy is what percentage of the predictions are actually correct. And accuracy does not give you a good sense of your model in a lot of cases. For instance, if you were trying to do some kind of fraud detection, your model will always be very accurate because probably 98 or 95% of your data belongs to one class, which is not fraud. So in that case, also something like precision would be very important. And when you have multiple classes, it is also important to look at precision, recall, accuracy per class. The next thing I want to talk about is confusion matrix. So confusion matrix is like a matrix that gives you a sense of the correlation between classes. This is particularly useful if you have multiple classes, and then if you are trying to figure out which classes are very correlated. So for this, I chose this example where you have these multiple classes, apple, banana, bell pepper, burger, etc. And you try to see like where is the weight in the off-diagonal elements and why is the model failing. So it's very useful for doing like a deep dive. And here you see that pomegranate and burger, or sandwich and burger, are confused very often, which again is not surprising. And then apple is, well, sometimes apple is mistaken as tomato. And we can see why this would happen. Both of them are fairly round. And we see some of the cases where all of the cupcake is classified as cake, or green salad, which is very interesting. Cake makes sense, but green salad does not. So here, like, it just gives you a sense of, what classes are correlated, but also where your model is going wrong. Maybe, you need more examples of green salad and cupcake to make sure that cupcake is not misclassified as a green salad. The other thing that I wanted to talk about was thresholding. So here again, I've taken the example of binary classification. So let's say you have a model, and your model says that this this patient for sure has a cancer, and it says I have 95% confidence that, or the probability of belonging to the class cancer is 0.95. So there you're sure it's that patient has cancer. But then it could also be that the model says that this is the probability of having cancer is 0.55. So at that point your model doesn't know. So you could design a system where after your model has a threshold higher than 0.75, you could say this is a positive class. But then when the model predicts between 0.3 and 0.75, this is an area where the model is incapable of making a decision. So for this area, we're either going to go through like a human process, or for this amount of data, something else needs to be done. And this helps in cases where you really need a model that has high accuracy and you cannot afford to make mistakes, like the fraud detection case. And I think I will stop here and go to my final slide. So we have like a few minutes for question answers. So finally, what I'd like to say is a lot of advances have been made in computer vision, and that's my timer actually. So a lot of advance has been made in computer vision. Sorry about that. So, and the nice part about that is that most of this advance is available to us. That is, it is available to us in the form of pre-trained packages, which we can use. The other thing that's interesting about computer vision is that not doing deep learning is actually much harder than doing deep learning. So in other fields, very often I have gone through the process of doing like a simpler model and then doing deep learning. But here the deep learning models are packaged so well that it's just like the first thing to do. Another important part to remember is that it's important to collect good quality, high volume training data if you're trying to get to a good model. Otherwise, you'll be in a state of garbage in, garbage out. So it's important to spend some effort in that direction. And then defining your project well and measuring metrics correctly is very important for success in real life. And finally, there are just modules out there which can be used out of the box, which make like working in this space much easier than it was before. So yes, that's it.
Awesome. Thank you so much